Hello, I Anand Jain from Hanumangarh, Rajasthan welcomes you to your favorite Shridevi Classes YouTube channel, and on behalf of channel we wish you a very happy new year 2023. Today in our class 12th physics playlist, in our chapter electric circuit, we will study construction and working of meter bridge, and we will study both theoretical and practical part of meter bridge operation. We will also solve some numerical problems for our exam preparations. Let's start. In this part of circuit, 5 resistances P, Q, R, S and Z are connected among 4 nodes A, B, C, D in a typical manner in which no two resistance are in series or parallel to each other. So such circuit cannot be solved by series parallel simplification. But there exists a special condition of this circuit as studied by scientist Wheatstone, where node B and node D got identical potential conditions and potential difference across G resistance between B and D terminals becomes 0. So there won't be any current flow in this galvanometer section, and a galvanometer with null deflection indication can confirm this particular balanced condition of Wheatstone bridge. And in balanced condition, as B and D got identical potentials, A is a common point. So potential difference across P resistance in AB section with current X in P resistance XP become equal to potential difference across R resistance with Y current YR. Similarly, C is a common point and B and D got identical potential. So potential drop across Q resistance with same X current, as central branch won't have any current. So current of P resistance X passes directly in Q resistance, and voltage drop XQ become equal to voltage drop of S resistance from Y current of R resistance YS. From these two equations, if we take ratio of Y to X current, then from first equation it is P resistance to R resistance, and from second equation it is Q resistance to S resistance. And this balance relation of Wheatstone bridge can be rewritten as PS equal to QR. That means product of resistance values of opposite side resistances P and S become equal to other opposite side pair Q and R values. So PS equal to QR become the balance equation for such Wheatstone bridge when center branch got zero current condition or null deflection in galvanometer. Meter bridge or slide wire bridge is a particular form of Wheatstone bridge circuit. In construction, it consists of a wire AB of exactly 1 meter or 100 centimeter length. This wire is made of an alloy material, either constant or manganese, having low TCR and high resistivity. All through the length, this wire got uniform cross-section area. This wire is stretched between two L-shaped copper strips with two terminals marked as A and B. A meter scale of 100 centimeter is also fitted adjacent to this wire, parallel to wire length, to assess length of any position on wire from A. Now there is another copper strip C here and L section, and this flat strip maintain two gaps, one for known resistance and other one for unknown resistance, and suitable terminals are provided to connect those resistances. As a standard practice, in the left gap, a resistance of known value is connected across terminals. Practically, this resistance is in the form of a resistance box, and appropriate value is selected by selection of plug settings in a resistance box. And in right side gap, unknown resistance X is connected across terminals, whose value we have to determine. In this bridge circuit, a sliding jockey contact is provided on wire length. So this bridge is also known as slide wire bridge, and a sensitive galvanometer is used to find out balance condition of bridge, and one end of this galvanometer is connected to sliding jockey contact and another end of galvanometer is connected to the same strip which connect known resistance and unknown resistance together at position C. For circulation of current, external voltage source is connected across wire at terminal A and B with positive end connected to A side, and a one-way plug key is also used to circulate current only for that interval at which we are doing readings for measurement, and for rest of the time this open key condition of switch disconnect battery from the circuit. This meter bridge circuitry is now exactly the same as that of Wheatstone bridge circuit. This sliding jockey contact on wire length produce two resistances, one of L length resistance which become one ratio resistance of our Wheatstone bridge P, and the remaining length resistance become another ratio resistance Q, and we have known resistance R and unknown resistance X forming bridge with middle section is galvanometer section. And when this bridge circuit is balanced, a voltage excitation will produce identical potential at junction C and D, and zero potential difference across CD section produce zero current in this galvanometer branch, and a sensitive galvanometer show null deflection position for balance condition of bridge. And in this balance condition, this L length wire resistance P and unknown resistance have a multiplication value equal to product of these two resistance of remaining length and known resistance as shown in magenta ellipse. So when product of two opposite resistances in the bridge matches with each other, then we say bridge is in balance condition, and in that balance condition we can compare known and unknown resistance in terms of balance length and remaining wire length. To check whether this meter bridge circuit is properly operational, to check proper connection of all resistances and source battery and regular functioning of this meter bridge circuitry, we place sliding jockey contact very close to terminal A on wire, and due to imbalance, galvanometer will show deflection in one direction, and the same jockey contact when placed to other end of wire B, the galvanometer should show deflection in opposite direction. If these two opposite deflections are given by galvanometer, then we can say that there is all connection in proper conditions and circuit is properly in function. If in both directions there is only one direction of deflection, it means somewhere some loose contact exists and we have to correct that. Two opposite direction deflection near A and near B position of jockey contact on wire by galvanometer indicate proper functioning of meter bridge circuit, and there must be an in between length position where zero current condition in galvanometer is shown by center zero null deflection position, and we'll say that at that condition this Wheatstone bridge circuitry of meter bridge is in balanced condition. For comparison of known resistance R and unknown resistance X, the known resistance in the form of resistance box is connected in left gap and unknown resistance is connected in right gap. Across two ends of wire AB, voltage source with plug key switching is placed, and sensitive galvanometer is connected between C and sliding jockey contact D on wire. Now cell circuit is closed and sliding jockey contact on wire is adjusted to a certain length position from A such that galvanometer show center null deflection position. Now this condition is known as balance condition of bridge, and in this balanced meter bridge condition, this length of jockey position from A is known as balance length, and let it is L. So the remaining length of wire, if L is in centimeter, then remaining length is 100 minus L centimeter. As this meter bridge circuit is in balance condition, so as per Wheatstone bridge principle, in balance condition, if this sliding jockey contact divide this wire resistance in two ratio resistance P and Q, then the product of P with unknown resistance X become equal to other opposite sided resistance, the ratio resistance Q of remaining length, and R, or we can say ratio of P to Q resistance is equal to ratio of known resistance and unknown resistance, and we know P is this AD section wire length resistance, and if this length is L and per unit length resistance is small r, then L length of wire got resistance LR and the remaining length got other ratio resistance Q equal to 100 minus LR, and if we substitute value of P and Q as LR and 100 minus LR, and resistance per unit length will get cancelled out. So we can make comparison of known resistance with unknown resistance without knowing the per unit resistance value of this slide wire. The only requirement is all through the length, the per unit length resistance should remains the same, and for that the wire should be of same resistivity all through the length, and it should have same uniform cross section area all over the length. Now this relation can be modified as unknown resistance is equal to known resistance multiplied by 100 minus L length divided by L length. So we can say known and unknown resistance got the same ratio as this sliding jockey contact produce ratio of lengths L and remaining length 100 minus L. So by the knowledge of balance length L and known resistance, we can find out unknown resistance X. Now such Wheatstone circuitries produce most sensitive measurement and can distinguish a slight amount of imbalance when the balance length is near middle side of this wire length, or balance length L is near 50 centimeter positions. Or to get value of unknown resistance, we select a standard resistance of value almost of the same order. So in that case, our bridge become most sensitive in measurement. This numerical example will explain the theory of meter bridge circuitry. In an experiment of meter bridge, to measure unknown resistance, we select 8 ohm value in standard resistance box and obtained balance length equal to 45 cm from position A of sliding jockey contact. We have to determine the value of unknown resistance, and in the second part, we have to determine this balance length if we interchange the position of known resistance and unknown resistance in these two gaps. So in first case, at balance condition, the resistance of balance length wire LR and remaining length resistance 100 minus LR got the same ratio as that of known resistance and unknown resistance, or unknown resistance is obtained in terms of balance length L and known resistance R, since balance length is 45 centimeter and 100 minus 45 centimeter will become 55 centimeter, and known resistance is 8 ohm, and if we simplify this relation, then we'll get unknown resistance equal to 9.778 ohm value. Usually we place standard known resistance in left gap and unknown resistance is placed in right gap. But if the two resistances are interchanged in position, then in that case, the ratio of balance length and remaining length got the ratio of left gap resistance, which is unknown resistance, and right gap resistance, which is known resistance. Unknown resistance we have obtained as 9.778 ohm and known resistance is of 8 ohm value. If we cross multiply, then 8L become 9.778 multiplied by 100, that is 977.8, and minus 9.778L, and if we change side of this negative term from right to left, it will add it together, and addition of 9.778 and 8 become 17.778L, and the right side got a number 977.8, and simplification will result in length L as ratio of 977.8 divided by 17.778, and it is 55 centimeter. So it is clear that 8 and this 9.778 resistance got a ratio of 55 to 45, or 11 by 9. The ratio of length at two sides of this slide contact are in the same ratio as that of these two resistance ratio. This textbook numerical problem is very important from examination point of view. In a meter bridge experiment, the balance condition or null deflection in galvanometer is obtained when sliding jockey contact have a balance length of 60 cm from terminal A on wire for one unknown resistance X and another resistance R. The value of this resistance R is not known to us, so we cannot determine the value of unknown resistance X straight away as we have obtained in previous example, but we can get the ratio of two resistances from this balance length information and remaining length calculation of 40 cm. Now in the same example, it is given that a known 12 ohm resistance is connected across R in parallel, and that will reduce parallel equivalent resistance of this combination from R value to some lower value, and with this new value of resistance in meter bridge experiment, the same unknown resistance is now got a balance length of 50 cm. We have to determine the value of both unknown resistance as well as other resistance used in left gap R. So in first case, as per balance condition of Wheatstone bridge, the ratio of two resistance in left gap and unknown resistance in right gap got the same ratio as two lengths at two sides of slide contact. This length is 60 cm and remaining length, the total length is 100 cm. So remaining length is 60 less than 100, 40 cm, and it means the unknown resistance is 2/3 of known resistance R, as these two lengths got 2:3 ratio. Now in case 2, when 12 ohm is connected parallel to R, the new equivalent resistance in left gap will become product by sum 12R divided by 12 plus R ohm. Now in this balance condition of meter bridge, where balance length is 50 centimeter when 12 ohm is connected in parallel to R resistance. The ratio of right gap resistance and unknown resistance in left gap got a ratio of two lengths. So one length is 50 and the remaining length 100 minus 50 is also 50. So the two length got 1:1 ratio. So the two resistance also have 1:1 ratio. So unknown resistance X is equivalent to parallel equivalent of R and 12 ohm. Whereas in previous case, the balance length and remaining length got a ratio of 3:2. So this R and X got 3:2 ratio, or X is 2/3 of R. And if we equate two value of unknown resistance, then R dash, which is parallel equivalent of 12 and R, product by some calculation, and X is also from previous experiment 2/3 of R, then equality relation from these two conditions will become this yellow highlighted relation. This numerator R from both sides get cancel out. 12 3s are 36, 12 2s are 24 and 2R, and 24 when transferred to other side will get subtracted from 36. The difference is 12, and when divided by 2 we get the value of R equal to 6 ohm, and from this relation we can obtain the unknown resistance X equal to 4 ohm. This slide wire bridge or 1 meter long wire length bridge, meter bridge, is very convenient to compare unknown resistance with standard resistance box resistance in medium resistance measurement ranging from 1 ohm to 1 mega ohm. But in this meter bridge measurement we have some limitations and some precautions are required during measurements. Let's discuss them one by one. In this meter bridge circuit we have assumed that these thick copper strips which we have used to connect resistances got negligible resistance, but in actual practice they have a small amount of resistance and which may produce error in our measurement. Now to compensate these errors we can make average of two measurements which are obtained by interchanging the position of left and right gap resistances mutually, and averaging of the two results will compensate error caused by connection and contact resistance. For better quality, higher accuracy and more precision measurement, in place of simple meter bridge we can use either Carey-Foster bridge or Kelvin double bridge. Normally for small resistance measurement of magnitude less than 1 ohm we use Kelvin double bridge. In meter bridge, this slide wire and standard resistance of resistance box are all these resistances are designed for short time current reading. So this cell is connected to circuit by this key only for a short duration for measurements only, and a continuous current flow in these circuit component may overheat and damage them. To obtain balance condition we have to slide this jockey contact gently on wire length. A hard press of jockey contact on wire may change or alter cross section area of wire at some positions, and that will alter uniformity of wire resistance per unit length all through the length and produce error in our measurement. If slide wire and other standard resistances are made of constant alloy and connecting strips and connection wires are made of copper, then copper and constant junctions form a thermocouple, and if thermocouple loop have two different temperature at two junctions they produce a small amount of thermo EMF, and that thermo EMF either may add or subtract this battery voltage and produce error in our measurement in this bridge circuitry. To compensate such error of thermocouple we take geometric mean by two readings, and second reading is obtained by interchanging cell terminal, so that one polarity of cell connection to circuit, if thermo EMF are supporting, then in another connection they may oppose cell voltage, and geometric mean of two reading will compensate thermo EMF error. We have explained construction, working and all theoretical and practical aspect of meter bridge measurement, and we have also solved some exam like problems. Our other learning video of class 12th physics are equally useful in your studies, and you can increase your subject understanding and scoring ability in exam by these learning videos. If you want online doubt clearing support from Shridevi classes with dedicated exam centric notes, do join membership of Shridevi classes by clicking join button just beneath. Happy learning, have nice time. Thank you very much.